Our project title is a single stage quasi resonant inverter for grid-tied photovoltaic systems. Actually, this is a R&D project. Introduction. The single stage topology can handle PV strings with the different electrical parameters, locations and orientations. The inverter can obtain maximum possible power of each string independently. The HF link, which is formed by an AC inductor and small AC capacitor, is responsible for transferring power to grid along with creating zero voltage switching. It provides high power density, high reliability and high efficiency. The main objective of our project is to achieve AC from the renewable source through quasi-resonance components to make a ripple-free parameter existing system. In single-stage PV inverters, a transformer is used for boosting the input voltage. The input voltage required is higher than the grid voltage. The energy storage needs to be at the front of a single-stage inverter, and it is usually implemented by electrolytic capacitors. The PV panel's characteristics changes all the time, which is not good for PV applications. This is existing block. The input is given to DC converter and then given to ceiling where the quasi resonance is created, and the output is given to DC to AC converter, then it is applied to the grid. Drawbacks: it has short lifespan, limited frequency response, high level of leakage and ripple current is high. Proposed system: we implement quasi-resonant inverting, zero current switching and zero voltage switching. Actually, quasi-resonance is allowed to occur just before and during the turn on and turn off process to create ZVS and ZCS condition. In ZCS, the turn on and turn off will occur at zero current, whereas in ZVS, turn on and turn off will occur at zero voltage. It is applicable for constant load applications and it is off-time control, whereas ZCS is on-time control. The charging time of capacitor is reduced. HF AC link is formed without the use of bulky short-life electrolytic capacitors. Total harmonic distortion is improved. This is our proposed block. Input voltage is given to DC to AC converter. The output voltage and the reference voltage is combined and then given to linear voltage control, where the steady state output voltage is obtained. Here the linear voltage controller is used to provide a constant DC voltage regardless of changes in load current. This current and induction current from DC to AC converter is fed to inductor current controller, where it arrests the ripples and voltage will be increased. Hence the current will be controlled and the switching signal is again given to DC to AC converter. HF AC link. It is formed by an inductor and a small AC capacitor without the use of bulky short-life electrolytic capacitors. Inductor L is used for handling power from the PV strings to the grid. Capacitors C generate partial resonance to achieve soft switching. Solar panel. It uses light energy from the sun to generate electricity through photoelectric effect. Actually, photoelectric effect is the emission of photons or electrons due to incident light. Each module is rated by its DC output power under standard test condition. It ranges from 100 to 320 watts. A single solar module can produce only a limited amount of power. Specification: the rated maximum power will be 300 watts, open circuit voltage 180 volt, maximum power voltage 30 volt, maximum power current 2.3 amps and short circuit current 2.8 amps. Quasi-resonance. Quasi-resonant converters use the tank circuit to create either a zero voltage or zero current condition for the power switch to turn on or turn off. The resonant voltage across the tank circuit on the DC input voltage generates the zero voltage condition for the switch to turn on. The superposition of the resonant current flowing through the tank circuit generates the zero current condition to turn off the switch. Features: it has high safety degree under short conditions. It has drain capacitance to generate a zero voltage condition. Turn on losses of the MOSFET can be minimized. Snubber circuit. It provides a necessary protection to the MOSFET through snubber circuit. It is a series combination of resistance and capacitance. A diode is connected in parallel with resistance to reduce the charging time of capacitor. Thus, it gives a path to the capacitor to charge quickly in order to reduce the time constant. This is our simulation diagram. It consists of a protection circuit, an inverter circuit, voltage regulator. The input DC is given to the circuit. The inductor and capacitor act as a filter circuits. It filters the unwanted signals and given to the protection circuit. The voltage will have both the positive and negative flow. Hence, in order to prevent the circuit or MOSFET from the damages, we use protection circuit. Quasi resonance is created and alternative MOSFETs will get turn on and turn off. Thus, the DC is converted to AC. This is our simulation output. When the capacitor is used before the occurrence of quasi resonance, the simulation output will be like this. When both inductor and capacitor is connected, quasi resonance is created and the output will be this. Software requirements, MATLAB and Simulink. This is our hardware kit. The components used here are inductor, capacitor, MOSFET, diode and measurement tank circuit. The input DC is obtained from the solar renewable source and battery. MOSFET acts as an inverting circuit. Inductor and capacitor will be used for filtering purpose. Inverting circuit has both the positive and negative flow. During negative flow, backflow voltage occurs and it may affect the multistring. To prevent the multistring while backflow voltage, a protection circuit is used. It consists of 4 clamp diodes to tap the reverse voltage. Resonance is created across the inductor and capacitor when a system is able to store and easily transfer energy between 2 or more different storage modes. Soft switching can mitigate some of the mechanism of switching losses and reduces the generation of EMI. During the occurrence of quasi resonance, zero voltage switching takes place and turn on the transistor. ZVS is usually preferred in converters. Thus, ZVS eliminates switching losses induced by diodes and store energy, the output capacitors. Thus, the DC is converted to AC. Hardware requirements: solar panel, battery 12 volt, inductor 40 mH, capacitor 22 picofarad, pulse transformer, driver circuit, MOSFET and diodes. Advantages: fall and rise time of both voltage and current waveforms are negligible. Switching losses is less, reduces EMI, reduces ripple. Conclusion: the control scheme and the ripple-free parameter of proposed inverter has been described. Thank you.